Hey, hello everybody. Hello for this next Wednesday's session. Today we'll be starting with Maxim's talk on accelerating Synproxy with XDP. And as usual, we will take questions at the end, but you can continue typing your questions in the Q&A tab and comments on chats maybe, and you can also raise hands so that we can bring you on stage. But we'll attend to questions after the Maxine video is played on the talk. Welcome, Maxine. I think I'm going to start the video. Okay.
Yeah, let's start it.
Yeah.
Hello everyone, I'm Maxim from NVIDIA, formerly Mellanox, and I'll present our solution for accelerating Synproxy with XDP. I'd like to give credit to Ronnie and Yossi for the architecture, and also thank Noam and Yossi for help with performance evaluation. In today's talk, I'll go over the Synflood attack itself, its dangers, and the way to mitigate it, and I'll define the threat model. Then I'll define the use case of a firewall that protects the server from this attack. Finally, I'll present our solution to accelerate the firewall with XDP, and we'll see performance numbers. So, the first section is dedicated to the Synflood attack. As our solution is a security means, it's important to define a threat model and identify the attack vectors that we aim to mitigate. So, we have a TCP server exposed to the internet, and an attacker wants to disrupt its service by exhausting its resources using DDoS. We assume that this attacker is not a man in the middle, because otherwise there are simpler ways to disrupt traffic. Just block it or send RST packets. Also, in this talk, we are not considering such vulnerabilities as buffer overflows or other exploitable programming errors. Classical DDoS techniques, such as bandwidth saturation attacks, can generally be mitigated by rate limiting per source IP address. However, Synflood is a special case, and such mitigation doesn't work, because the attacker can spoof the IP address. Hence, a different way is needed to address this attack. In this talk, we'll focus on Synflood mitigation. Let's define some terms which will be used a lot in these slides. Since we are looking at the attacker in context of Synflood, a malicious client will be one who attempts to deploy Synflood or disrupt our mitigation solution. Even though a client can do other kinds of malicious actions, for example, open a lot of connections, doing the whole three-way handshake, such clients will be considered legit in scope of this talk, because other mitigations, such as rate limiting, work in such cases. This slide describes the Synflood attack. As TCP connection establishment is stateful, it's enough for a client to send the SYN to make the server allocate resources. A malicious client doesn't care about receiving a SYNACK reply, so the attacker can spoof the source IP address to circumvent possible limiting of rate of connections per source IP. Moreover, it's a fairly simple attack because it's very easy to generate SYN packets. This whole thing leads to the following consequences. By spoofing IP addresses, the attacker circumvents any rate limiting and easily fills up the socket's backlog queue with half-open connections, leading to denial of service for legit clients. The classical approach to mitigate this attack is to avoid allocating resources for malicious clients. The only reliable way to distinguish them from legit clients is by checking whether they respond to the SYNACK, which means the first stage of the three-way handshake must be stateless. Of course, the solution must not expose new attack vectors. So, such classical approach is syncookies. Instead of storing the state on the server, it makes the client remember the server state for it. The state is encoded in the sequence number and timestamp, and sent back to the client with a SYNACK. It's called syncookie and timestamp cookie correspondingly. Legit clients send the state back with the first ACK, and the server can decode it. Moreover, this state includes a cryptographically secure hash, which the server can use to verify that the cookie was issued by this server to this client. After verifying that the client is legit and decoding the cookie, the server can allocate resources. Let's see if syncookies expose new breaches. First of all, we send the SYN-ACK to a potentially spoofed IP address, which hints us on possible amplification attacks. In such attacks, the attacker sends a low amount of spoofed traffic to the server, making it reply with bigger amount of traffic to the victim. Luckily, the SYN-ACK size is about the same as the size of a SYN, and both are a single packet, which makes it basically pointless for an attacker to deploy such an attack. It can attack the victim with the same bandwidth directly. More important is that the server now allows to open a connection with an ACK packet. However, it's not possible to calculate a SYN cookie purely on the client side without receiving a SYN-ACK, because the client doesn't have the server's secret value used for the hash. Also, the hash includes a timer to prevent replaying. Essentially, this means that SYN cookies successfully mitigate the dangers of Synflood without opening new security holes. Unfortunately, SYN cookies are not ideal and have drawbacks. The first one is minor. SYN-ACKs are not retransmitted if lost, but it's not a big deal because a legit client will retransmit a SYN. More important is that some information is lost. MSS is encoded in 2 bits, losing precision. Client's initial sequence number is not stored. And if the client doesn't support TCP timestamping, some even more important information is lost. SAC permission, window scale, and DCN support, which will affect the performance of the connection. Additionally, there is no reliable way to detect loss of the client's first ACK and ask for retransmission. If it happens and the server receives the second ACK, it will try to check the SYN cookie for it. Due to the specifics of Linux implementation, which encodes the client's initial sequence number in the SYN cookie, the server will either drop the connection or, if the lost packet is not bigger than 3 bytes, the connection will survive, these few bytes will be lost, and the MSS value will be decoded incorrectly. More information is available by the link below. However, I'd like to say in advance that this drawback is not applicable to Synproxy and our solution based on it. So enough about the attack. Let's talk about our Synproxy use case. It's a firewall that stands before the server, generates SYN cookies on behalf of the server, mitigating Synflood, and hiding the fact of the attack from the server. When a client sends a SYN, the firewall generates a cookie and replies with a SYN-ACK, also setting TCP window size to 0. Only after the client sends an ACK, the firewall opens a real connection to the server and does the 3-way handshake. This ACK can't contain any payload because the window size was set to 0. After the firewall successfully establishes the connection to the server, it sends another ACK to the client with non-zero window, permitting sending data, and establishes bidirectional data transfer. Since the firewall cannot control the server's initial sequence number and initial timestamp, they will be different from values sent by the firewall to the client. The firewall ends up proxying all traffic and rewriting server sequence numbers and timestamps, shifting them by a delta. Such solution already exists, and it's implemented as an IP tables module. It allows to build the firewall described in the previous slide and avoid wasting the server's CPU time on generating and checking SYN cookies. All the drawbacks of SYN cookies still apply, except the adverse effects of dropping the first ACK because it can't hold payload. On the other hand, there are a few other inconveniences. The latency of connection establishment is increased due to blocking the client from sending data until the final connection is established and another ACK is sent to the client. Also, Synproxy needs to know in advance the server's MSS and window scale. Synproxy was developed with performance in mind, and it optimizes out heavy operations like contract modification until it proves that the client is legit. The link below points to a talk by Jasper from Red Hat, which contains more details about Synproxy. However, XDP can still optimize generating and checking sync cookies by doing it early in the packet processing pipeline and saving time that would otherwise be spent on creating an SKB and going through the networking stack and IP tables rules. Since these operations are stateless, XDP is a good fit. Such an optimization increases the packet processing speed, making the firewall more resilient to stronger attacks. Alternatively, the firewall can run on a lower-end machine, such as DPU, data processing unit, inside the NIC, without sacrificing the baseline performance of Synproxy. So let's finally talk about XDP acceleration. The block highlighted in this picture will be accelerated with XDP. It includes all the stateless operations, generating a sync cookie and checking it. Synproxy is no longer involved at this step. Only after the XDP program checks the sync cookie in the ACK packet, it passes it to Synproxy, and the rest is handled by it as usual. This slide shows the algorithm inside the XDP program. First, it checks whether the packet is TCP or not. If not, it returns XDP pass immediately. The next step is to query contract. If the packet belongs to an established connection, the program returns XDP pass, and there is nothing it should do here. If it's an unknown connection, it can be a SYN packet, an ACK packet of the handshake, or another unexpected and probably invalid packet, which we will drop. If the packet is SYN, we need to generate a SYN cookie and a timestamp cookie, prepare a SYN ACK, and return XDPTX. If the packet is ACK, we check the SYN cookie. If it's valid, the packet is passed to the networking stack and Synproxy. Otherwise, we can drop it or even send back an RST. The whole thing sounds good until we realize that a few features are missing from the kernel. We have two helpers for sync cookies. However, they only work for local listening sockets and are not suitable for Synproxy. Also, there are no helpers to generate timestamp cookies and query contract. More information about the existing helpers is available by the link below, which points to work done by Google, but we're gonna introduce new helpers. This slide shows 4 new helpers needed for the XDP program to work. This list includes a helper to look up connection status in contract, helpers to generate a sync cookie and timestamp cookie without depending on a socket, and a helper to validate a sync cookie without depending on a socket. These helpers were implemented and are being prepared for upstream submission. Finally, let's review the performance of the XDP accelerated solution. To measure the performance of the firewall, we deployed a setup of 2 machines connected back to back. The left side generates good and bad traffic and sends it to the firewall on the right side. The firewall filters out malicious traffic and proxies legit traffic to the server that also runs on the left side. The traffic generator and the server are isolated on the left side, and we make sure the left side doesn't become a bottleneck. The whole packet processing on the firewall machine is confined to a single core. You can see the CPU and NIC model on the slide, as well as single core performance of XDPTX on this machine, which is provided as baseline and theoretical maximum. T-Rex generates SYN and ACK flood, HTTP perf generates legit traffic, and Nginx is the web server under attack. All numbers will be provided for a single core test. First, let's look at the packet processing rate in 2 cases: generating SYN cookies under Synflood and checking invalid SYN cookies under ACK flood. As we see, XDP accelerates both operations by a number of times. The XDPTX and XDP drop theoretical maximums stay higher because the real XDP program does much more processing of the packet. The next few slides show performance under 10,000 legit connections per second and the Synflood of an increasing rate. This plot shows the performance of non-accelerated Synproxy. Please note the logarithmic scale of the x-axis. Two lines show the number of established legit connections and the number of SYNAC replies to malicious SYN packets under an increasing Synflood. The amount of Synflood that Synproxy withstands without severely impairing the service is at about 300,000 packets per second. Adding an XDP program to the pipeline changes things dramatically. Not only this solution can send back about 7 times more SYNAC packets, but it also shifts the dashed line to 2.1 million packets per second, which means that the reliable service remains up until 2.1 million packets per second of flood. Comparing the plots for Synproxy and XDP, we can clearly see how XDP outperforms plain Synproxy. Please note that this plot uses the logarithmic scale also for the y-axis. XDP successfully mitigates the attack of a much larger scale. And while being under attack, XDP also assures reliable service for the legit clients under an attack of a larger scale. Our final test will show how susceptible the firewall is to the ACK flood. As connections are opened with an ACK packet and checking the SYN cookie takes CPU cycles, it's important to understand at what point ACK flood with bad cookies could disrupt the service. As we see on this plot, XDP also accelerates this operation, keeping the service reliable until a much bigger flood, 3 million packets per second compared to 600,000 packets per second with plain Synproxy. As a conclusion, I'd like to say that mitigating Synflood is another job that XDP does well. The solution is based on Synproxy and allows to increase performance of its bottlenecks without requiring changes to Synproxy itself and allowing for easy integration. The kernel patches are being prepared for upstreaming, and this slide contains all the link from the presentation. Thanks for your attention. If you have any questions, you're welcome to ask.
Great presentation. We do have some questions. Let me just put them on stage.
Okay, so if the attacker can, I guess, replay hacks, send them again, proxy will create too many sins to the server, so it will receive cookies from the stack, isn't it? First of all, okay, let me clarify some things. First of all, the SYN cookie itself contains the hash of a few values, which include the 5-tuple, the server secret, and also the slowly increasing timestamp. So, first of all, what prevents replaying the same acts is the 5-tuple itself, because after you use the 5-tuple, you used up your source port, and you cannot open a new connection with the same 5-tuple before the previous one closes. And if you wait until it closes, then the timestamp, this timer will increase, and the cookie will also no longer be valid. Another thing I want to also clarify is that we receive cookies from the stack with SYN packets, not with ACK packets. So the whole purpose of this Synproxy is to generate cookies on behalf of the server. We do not ask the real server to generate cookies. We generate our own cookies on the firewall side. And it happens with a syn. If we just send an ACK, we need to somehow craft the right cookie, which shouldn't be possible because the server secret is only known to the server. Like in this case, the server secret is the firewall's secret, actually.
I'm going to invite Ivan to the stage. 1 second. I think he has a follow-up.
Okay.
Do you hear me?
Yeah, I can hear
Yes.
you.
Okay. I mentioned the other scenario. So not when attacker sent you some forged traffic with some IPs that doesn't belong to him, but when the attacker is some botnet of I don't know, of some web cameras, and they are constantly trying to open a new connections to your proxy. So they actually are able to respond your scenes, scene X, and send X with a valid cookie value. And then it might create a wave of such valid X to your proxy. And in this case, a proxy will create another wave of scenes to host to the kernel, yeah. And kernel will realize that there is a scene attack on the socket behind the firewall, and it will create cookie challenge for firewall, and your firewall will need to pass this challenge to actually.
Okay, yeah, now I think I get to your scenario. So, like, even if the server also wants to use syn cookie protection, that's not a problem because it's fully transparent to the client. The client in this case is this Synproxy, but the whole idea is to not to go to this stage. And the attack scenario that you described, when all the attackers have real IP addresses, non-spoofed, but they try to open a lot of connections, it should be mitigated by other means, specifically by rate limiting the number of connections per source IP address. So if you deploy such protection, then your scenario will not be possible.
Okay, and I have another one question. So when your proxy actually proxies scenes, so it actually catch a connection on its sides and opens a new one with the host side. So you need to somehow either synchronize sequence number sent from your server to the end client, to the legit client, or either you need to change them on the fly when you are sending in traffic. So it's either some synchronization point, either it is performance hit on the hot path. So another solution, what was actually described in that Google paper you mentioned, it was somehow to synchronize the result of passing cookie with from the XDP program to the kernel stack, and to create a new connection directly in kernel without adding new connections, or open new connections between firewall and host. So it seems like more promising than moving from API tables to XDP.
Okay, so let me answer this. Well, I think the two things that you described are not relevant to each other because, yes, you're right that Google mentioned some missing piece of the puzzle, especially passing the result of checking the sync cookie in the ACK packet to the stack. This is also missing in this solution because there is no such a mechanism currently, and something probably could be created, but it needs to be designed properly. Yeah, this solution also suffers from checking sync cookies in the ACK packets twice, although it only happens for legit clients, which should not be some bottleneck when under the attack. But even if you had such a mechanism, I don't see how it would prevent you from doing sequence number rewrites. So as I mentioned briefly in this presentation, yes, we are doing shifting of the sequence numbers by some delta because we don't know in advance the server's sequence number. This is actually the code which already exists in Synproxy in this IP tables module. It's not part of the XDP program, like it's something that already exists. So yeah, we leverage this functionality to shift the sequence numbers. But even if you were able to pass the check result from XDP to networking stack, it wouldn't help much. Like consider, for example, bare Synproxy without any XDP. It still has to do this rewriting of sequence numbers just because the algorithm is that it opens the new connection only after it receives an ACK, and at that stage the connection between the proxy and the client already has some initial sequence number. So does that answer your question?
Thank you.
Okay, thanks.
So I'm going to, I don't know if I'm getting them in the right order, but let me show you the next question.
Okay, seems these new helpers could have been calls to kernel functions directly. Was this considered during development? This is a BPF feature that was merged very recently. Yeah, I am aware of this new BPF feature. However, the development started before this feature landed. And to be honest, I still didn't get myself closely familiar with this BPF feature. But that's certainly something that we could consider in future development, because like we plan to submit this work, and the new BPF feature is has landed. So we will need to reconsider if we need new helpers or if we could call kernel functions directly, and which approach will be better. So thanks for this hint.
Thanks for the question. If anybody wants to come to the stage, just raise your hands. Next question. Jamal, do you want to come on stage?
Have you considered running with a simple contract table that you maintain so as not run contracting? So do you mean like implementing some simple contract inside BPF instead of leveraging Linux contract?
Yeah, that's what I was asking, because there is some cost with doing contracting, right?
Yes, there is, and we actually did consider this option, but for simplicity's sake of the solution, we chose to leverage as much of existing code as we could, and as long as it fits, as long as it meets our performance target. So if we find out that in our particular use case scenario, we don't meet the performance target with Linux contract, we'll probably have to move the whole thing to BPF. And actually, I'm aware that there is some BPF-based contractor by Cilium. So this could be an option to further speed it up, because as far as I understand, this contractor is pretty mature, and redeveloping a similar thing from scratch would be a lot of pain. And we considered having some simplified contract, but we decided that like no valid simplification could be actually made. There are always some corner cases that we need to handle, and which are best handled by the existing contractor. But of course, as an acceleration, as a way to accelerate it even further, yeah, this is a valid approach.
Yeah, so I'm just, Tom, I noticed Tom asked on the Q&A if there's such a thing as simple contractor. So my response is, in this case, so yes, I agree with you. The contracting in NetFilter is very mature. It does a lot of things, does a lot of more deep packet.
Oh.
Oh, seems we lost Jamal.
Hey, sorry, that was me. Jamal, I'm sorry. Let me get you back on stage. And Roni, sorry, that was me.
Yeah, I don't think you can bring two people on stage. Only one. It's like a microphone, right? So there's only one person. Yeah. So yeah. What I'm so I'm jumping ahead and responding to Tom's comment. Tom made a comment as, is there such a thing as a simple contract? And my answer is, yeah, sometimes you don't need. So for example, the NetFilter contractor does a lot of very sophisticated things. It protects you against ACK sequence issues, etc., etc. In your case, I think what you need is you have 5 tuples, right, that you really care about. You look for that first syn packet, and then you could probably store some state and wait for the responses. In others, you don't need to, for example, run all the sophisticated algorithms that the NetFilter contracting has implemented.
The problem is that we also somehow need to track connection closing, because if the connection closes after the wait timeout, the same 5 tuple can be reused. And here some sophisticated stuff begins.
Okay, yeah. So you're talking about the time wait that may be a challenge at the end.
Yeah, so I'm not saying it's not implementable. Of course, it is implementable, and there are examples of BPF-based contractors. But for our purpose, we picked this approach, which leveraged a featureful contractor, which we had in NetFilter, and it worked for our performance goals.
Yeah, I understood. This is what's available, and and it's a lot more powerful. By the way, we also have implemented a contractor of some form, but very simple, the simplest one with 5 tuples on it.
Okay. Right. Actually, the thing is that such an approach allows you to integrate into some already existing firewall. For example, if you have more than just Synflood protection, you have some other IP tables rules, for example, and if you just attach this XDP program, you don't need to change the rest of the thing. You just accelerate one thing without sacrificing anything else. So that's another advantage.
Oh, okay, thanks.
Thank you.
So I think Roni wanted to get on stage. Roni, if you could just raise your hands, that'll be much easier for me to get you on stage. Or I'll have to find you. Roni? Okay, let me just invite you to stage right now.
So you hear me now?
Yeah.
Yeah, thank
Okay.
you. So sorry, grab the microphone from Jamal. It wasn't polite. Yes, so I wanted also to answer Jamal. I think the idea of what Maxim is doing is we don't want to copy all the code, right? Because there is also the handshake that you're doing, the Synproxy is doing and sending, and then ARC and getting the response and calculating the different numbers. So it's a lot of code. And I think, Jamal, you presented yesterday how much complicate is to work with the XDP and the validator to do all this code. So, and I think the nice thing on XDP is that you can benefit from the kernel, because if you bypassing all the kernel and you're doing everything in the XDP, I don't want to say it, but there is another kernel bypass that you can use if you're bypassing it all the kernel. The nice thing of XDP that you can still consume things of the kernel, right? Like as Maxi mentioned, we are also configuring the IP table with other limitations that we want to, from specific range of IP address, getting the fin in order to close the connection. So that's the reason I think we don't want to put everything in the XDP.
Let me see if there are any follow-ups for you. Okay. So since you both are here, are there any numbers of the DPU as well, or in the works? Jamal wants to be back on stage, but Roni, you'll have to be out. So
Okay, no problem.
so do you guys already have numbers for the DPU, or it's still in the works XDP?
We have some preliminary numbers, but I'm not ready to say like anything specific. The work is still in progress.
Yeah.
Okay.
But
Thanks.
there are also still good numbers, also in the
Yeah, of course. Yeah, the whole thing works
in the
for
lower
GPU.
CPU. Yeah, and that's actually the real reason why we did it, because when we moved to the Bluefield, which are much lower CPU, we must have some acceleration, and the XDP was the chosen one.
Yeah. Thanks, Roni. I will bring Jamal back on.
Okay.
Hey, sorry about that.
It shows both Roni.
Oh, okay, good. We're both on. That's good. Ronnie, you can say it. I don't know how that happened, but
Oh,
okay.
Okay. Did you have something to say?
Yeah, no, I was just commenting. I agree with Ronnie that the complexity of trying to squeeze code into eBPF makes it sometimes unappealing from that perspective. When you start writing complex stuff, it gets difficult. However, like since you quoted the presentation from yesterday, there are performance issues with NetFilter in general. That's the only reason I would push for. In your case, you just need to watch for the scene and the fin handshakes, basically, right? Nothing more than that. And you need to maintain state in between, right? And then, between the scenes, you can generate your cookies. May possibly need an extra table just for keeping track of who you sent requests for. You can put some flags. I'm not saying this is a bad idea. I'm just saying that there's possibly other opportunities to optimize this further.
So we more work together with Maxim to see how we're doing that. And as you can see in the presentation, you're getting the ARC and you need to generate it from each scene packet, right? And then you're getting the ARC and you need to generate 2 packets. So in XDP, you can't generate 2 packets from a single packet that you're getting, right? Because you need to send a packet back to the server and a packet to the client, to the real client.
Mm-hmm.
So we had some ideas doing it with eBPF, not XDP, with TC, and then you can have a TC with eBPF and then submit the packet, and then another redirect the packet to another port also.
Yeah, that makes
So
sense.
it's making you make how you understand how make it life complex. You need to have a program that is part of it is XDP and part of it is TC eBPF.
Yeah. We can have the conversation after, Ronnie. Thanks. And Maxim as well.
Thank you. Let me go to the next one. We have just 5 minutes left.
Okay, the next question was the performance hit of looking through the table of established connections in the XDP program. Well, we didn't measure particularly that hit, and I'm also not sure I get the question. The hit compared to what? To not going through the table, because we'll have to go through this table anyway, like either it be it in XDP or in the networking stack.
Yeah.
Maybe if possible, you could clarify what you want to compare against.
Maxim, didn't we had a test with the ACK also? Because this is actually what is happening when you get the ACK, right?
Yes, we did, and the performance numbers were in the slides. There was a plot.
So this is when you're looking on the table, right? And this is a small table at the end.
It's not only looking at the table; it's also checking the sync cookie, which means calculating the hash again. So also this operation. So it's not purely looking at the table. But like, yeah, of course, you can refer to the numbers in the slides for ACK-Flood. But I'm not sure, like when you compare performance of something, like you compare it to something. So if you want to compare performance hit of going through contract, what is the alternative we are comparing it to?
Synproxy without XDP.
Well, if it's Synproxy without XDP, which also goes through the same contract, then it's not a performance hit, it's a performance improvement in XDP.
Yeah. Okay. There's one last question. So, Maciek, if you have any, I mean.
Oh, I see there is some clarification. Yeah, as the next question.
Yeah, he has raised his hand. Yes, Maciek, let me just get you on stage. Somehow I can't get Ronnie off.
Ronnie is, has a VIP spot at the speakers. Yeah, I'm actually curious because the diagram that you showed that for every TCP packet you are going through the established connection list, and I'm curious if that has any negative performance hit on the flows that are actually established and for example transmit a lot of packets.
Oh, you mean for established flows? Well, okay, yeah. Now I get the question. So, that's a valid point. You mean that we'll have to go through this contract in XDP, but later on, when we pass the packet, the same contract lookup will happen also in the stack.
Yep.
Okay, so in order to do such a measurement, we actually need to run our XDP program and not run any attack and see basically maybe what's the throughput of the connections or what's the maximum number of connections per second will be with XDP program and without. I want to say we didn't do this particular test. It would be interesting to do so. But of course, yeah, you're right. The contract lookup takes time. However, it is anyway much faster than contract modification. That's one thing. And another thing, if we touch this contract entry in XDP, it will be hot in cache, and later on, when in a tiny moment the networking stack goes through the same entry, it will be already in the cache. So the performance hit is expected to be minimal, if even noticeable. But I'm not ready to say any numbers because we just didn't run this test.
Okay, sure. Maybe interesting follow-up.
Of course, it's an interesting follow-up. Yeah.
Thanks.
Cool.
Thank
Thank
you.
you. So there's one last question about the patches and repositories. It was covered in the slides, but Maxim, do you want to add anything? We're almost out of time.
Yeah, sure. So far the patches are not public. We are planning to submit them upstream, and I guess that will be the moment when you see them in public.
Yeah, it's covered in the slides. Okay, thanks everybody, and thanks Maxim. Thanks Ronnie.
Thank you. Thank you.
Yeah, bye.
Thank you.